Greetings to dear friends, thank you for choosing the BigDark channel for teaching scientific content. Please do not forget to subscribe, like, and comment to support the channel. Aurora. An aurora is also known as polar lights, Aurora Polaris, northern lights, Aurora borealis, or southern lights, Aurora australis, is a natural light display in Earth's sky, predominantly seen in high-latitude regions, around the Arctic and Antarctic. Auroras display dynamic patterns of brilliant lights that appear as curtains, rays, spirals, or dynamic flickers covering the entire sky. Auroras are the result of disturbances in the magnetosphere caused by the solar wind. These disturbances alter the trajectories of charged particles in the magnetospheric plasma. These particles, mainly electrons and protons, precipitate into the upper atmosphere, thermosphere/exosphere. The resulting ionization and excitation of atmospheric constituents emit light of varying color and complexity. The form of the aurora, occurring within bands around both polar regions, is also dependent on the amount of acceleration imparted to the precipitating particles. Most of the planets in the solar system, some natural satellites, brown dwarfs, and even comets also host auroras. Occurrence. Most auroras occur in a band known as the auroral zone, which is typically 3 degrees to 6 degrees wide in latitude and between 10 degrees and 20 degrees from the geomagnetic poles at all local times, or longitudes, most clearly seen at night against a dark sky. A region that currently displays an aurora is called the auroral oval, a band displaced by the solar wind towards the night side of Earth. Early evidence for a geomagnetic connection comes from the statistics of auroral observations. Elias Loomis, 1860, and later Hermann Fritz, 1881, and Sophustromold, 1881, in more detail, established that the aurora appeared mainly in the auroral zone. A geomagnetic storm causes the auroral ovals, north and south, to expand, bringing the aurora to lower latitudes. The instantaneous distribution of auroras, auroral oval, is slightly different, being centered about 3 to 5 degrees nightward of the magnetic pole so that auroral arcs reach furthest toward the equator when the magnetic pole in question is in between the observer and the sun. The aurora can be seen best at this time, which is called magnetic midnight. Auroras seen within the auroral oval may be directly overhead, but from farther away, they illuminate the poleward horizon as a greenish glow, or sometimes a faint red, as if the sun were rising from an unusual direction. Auroras also occur poleward of the auroral zone as either diffuse patches or arcs, which can be subvisual. Auroras are occasionally seen in latitudes below the auroral zone when a geomagnetic storm temporarily enlarges the auroral oval. Large geomagnetic storms are most common during the peak of the 11-year sunspot cycle or during the 3 years after the peak. An electron spirals, gyrates, about a field line at an angle that is determined by its velocity vectors, parallel and perpendicular, respectively, to the local geomagnetic field vector B. This angle is known as the pitch angle of the particle. The distance, or radius, of the electron from the field line at any time is known as its Larmor radius. The pitch angle increases as the electron travel to a region of greater field strength nearer to the atmosphere. Thus, it is possible for some particles to return, or mirror, if the angle becomes 90 degrees before entering the atmosphere to collide with the denser molecules there. Other particles that do not mirror enter the atmosphere and contribute to the auroral display over a range of altitudes. Other types of auroras have been observed from space, for example, poleward arcs stretching sunward across the polar cap, the related theta aurora, and dayside arcs near noon. These are relatively infrequent and poorly understood. Other interesting effects occur such as flickering aurora, black aurora and subvisual red arcs. In addition to all these, a weak glow, often deep red, was observed around the two polar cusps, the field lines separating the ones that close through Earth from those that are swept into the tail and close remotely. Auroral particles. The immediate cause of the ionization and excitation of atmospheric constituents leading to auroral emissions was discovered in 1960 when a pioneering rocket flight from Fort Churchill in Canada revealed a flux of electrons entering the atmosphere from above. Since then, an extensive collection of measurements has been acquired painstakingly and with steadily improving resolution since the 1960s by many research teams using rockets and satellites to traverse the auroral zone. The main findings have been that auroral arcs and other bright forms are due to electrons that have been accelerated during the final few 10,000 kilometers or so of their plunge into the atmosphere. These electrons often, but not always, exhibit a peak in their energy distribution, and are preferentially aligned along the local direction of the magnetic field. Electrons mainly responsible for diffuse and pulsating auroras have, in contrast, a smoothly falling energy distribution, and an angular, pitch angle, distribution favoring directions perpendicular to the local magnetic field. Pulsations were discovered to originate at or close to the equatorial crossing point of auroral zone magnetic field lines. Protons are also associated with auroras, both discrete and diffuse. Auroral particle acceleration. Just as there are many types of aurora, there are many different mechanisms that accelerate auroral particles into the atmosphere. Electron aurora in Earth's auroral zone, i.e. commonly visible aurora, can be split into two main categories with different immediate causes, diffuse and discrete aurora. Diffuse aurora appears relatively structureless to an observer on the ground, with indistinct edges and amorphous forms. Discrete aurora is structured into distinct features with well-defined edges such as arcs, rays, and coronas. They also tend to be much brighter than diffuse aurora. In both cases, the electrons that eventually cause the aurora start out as electrons trapped by the magnetic field in Earth's magnetosphere. These trapped particles bounce back and forth along magnetic field lines and are prevented from hitting the atmosphere by the magnetic mirror formed by the increasing magnetic field strength closer to Earth. The magnetic mirror's ability to trap a particle depends on the particle's pitch angle, the angle between its direction of motion and the local magnetic field. An aurora is created by processes that decrease the pitch angle of many individual electrons, freeing them from the magnetic trap and causing them to hit the atmosphere. In the case of diffuse auroras, the electron pitch angles are altered by their interaction with various plasma waves. Each interaction is essentially wave-particle scattering. The electron energy after interacting with the wave is similar to its energy before interaction, but the direction of motion is altered. If the final direction of motion after scattering is close to the field line, specifically, if it falls within the loss cone, then the electron will hit the atmosphere. Diffuse auroras are caused by the collective effect of many such scattered electrons hitting the atmosphere. The process is mediated by the plasma waves, which become stronger during periods of high geomagnetic activity, leading to increased diffuse aurora at those times. Some auroral features are also created by electrons accelerated by Alfvén waves. At small wavelengths, comparable to the electron inertial length or ion gyroradius, Alfvén waves develop a significant electric field parallel to the background magnetic field. This can accelerate electrons due to a process of Landau damping. If the electrons have a speed close to that of the wave's phase velocity, they are accelerated in a manner analogous to a surfer catching an ocean wave. This constantly changing wave electric field can accelerate electrons along the field line, causing some of them to hit the atmosphere. Electrons accelerated by this mechanism tend to have a broad energy spectrum, in contrast to the sharply peaked energy spectrum typical of electrons accelerated by quasi-static electric fields. In addition to the discrete and diffuse electron aurora, proton aurora is caused when magnetospheric protons collide with the upper atmosphere. The proton gains an electron in the interaction, and the resulting neutral hydrogen atom emits photons. The resulting light is too dim to be seen with the naked eye. Other aurorae not covered by the above discussion include transpolar arcs, formed poleward of the auroral zone, cusp aurora, formed in two small high-latitude areas on the day side, and some non-terrestrial auroras. Thank you for being with us until the end of the program. Be sure to mention your opinions about the educational video in the comments section.